Hello, welcome to this session. In the previous session, we looked at the noise transfer functions for different noise sources in a digital PLL, and we summarized that the TDC quantization noise and the power consumption is one of the problems in digital PLLs. So, now we would like to do something which helps us to reduce the effect of TDC's quantization noise. So, then we recall that in analog PLL we did not have any quantization noise while measuring the phase error, while here it has become a serious challenge. So, let us just compare the two. Analog PLL, when we had PFD, at that time the output of the PFD goes to charge pump output goes to an analog loop filter like this. Let us keep only one capacitor, and then you had a VCO. This is your feedback signal. So, in contrast to this, the digital PLL is something like this. You have a TDC which gives you quantization error. Actually, output of the TDC goes to digital loop filter, and digital loop filter I need to just put it in two parts, that is easier to understand. And then you have Ki plus here, and this with Z inverse, and it like this. You have the adder and so on. Output of this goes to your VCO, DAC and VCO. This is what we have. Now, we will make a distinction that the exact reason why we went to digital PLL. We went to digital PLL for the fact that this particular loop filter, including R and C, this capacitor was taking a lot of area, and well, current charge pump mismatch and resistance and so on, things were there. Okay. Here you can say that integration part of the capacitor is actually done by this block, or is very specifically speaking, it is done by this block. Okay. So, if we want to replace the capacitor, if we somehow just replace that particular capacitor part with the integrator, our area problem will be solved, right. But we have to give the digital bits, that is why we had TDC. Okay. Now, the TDC quantization noise which you are seeing at the output, right, that is mostly because of your proportional path gain. So, what transfer function did we have for our TDC? We had NTF of TDC as it is true that we added quantization noise here. Okay. This was our QTDC. So, this quantization noise NTF of TDC was KTDC by N. Well, this is just a constant here into loop gain by 1 plus loop gain. This closed loop transfer function, if you are looking at loop gain by 1 plus loop gain, the bandwidth of this closed loop transfer function is actually the unity gain frequency of your loop gain. It is very close to that. How? Well, you had loop gain as KTDC times your Kp plus Ki Fref by S times KVCO or KDAC times KVCO, which we wrote as KDCO over Sn. This was your loop gain. So, loop gain by 1 plus loop gain is nothing but 1 by 1 plus 1 by loop gain this. Okay, so I am just trying to give you the bandwidth by hand waving on this expressions. So, loop gain by 1 plus loop gain, this closed loop expression. This is as we wrote, this is 1 divided by 1 plus 1 by loop gain. So, I am going to have here s square n divided by your k TDC k DCO times Kp plus Ki times Fref. This is what we have. Okay. So, if this is the case that we have here, right, you can just look at it. This will give you a closed loop 0 also, okay, and we know that we had it earlier. So, KDCO times Kp plus Ki Fref divided by s square n plus KTDC, there is s here which we forgot, SKP. So, KTDC KDCO times Kp S plus KTDC KTDC KDCO times K I Fref. Okay. This is what we have. Now, we can have an approximation, and the approximation is that the two poles of these denominator, they are quite far away, and if the two poles of these denominators which is like ax square plus bx plus c, the poles of this quadratic equation x1 plus x2 is minus b by a. Okay. You have x1 x2 as c by a. If I assume that x1 is much larger than x2, okay, then I can say x1 plus x2 is approximately equal to x1, which is equal to minus b by a, and this implies that x2 is c by a whole divided by minus b by a, which is minus c by b. So, the two poles can approximately be found in this manner, which means that the two poles here from this equation, if the poles are far away in the closed loop, there will be KTDC, KDCO, Kp divided by n. This is one pole, okay, minus of this. Other pole is minus c by b, which is KTDC, KDCO, Ki Fref divided by b, which is here KTDC, KDCO, Kp. These two cancels. So, above transfer function which we have, that can be written as 1 plus loop gain, as you can just look at this value, right. What I can write here is as 1 plus s by omega z divided by 1 plus s by p1 and 1 plus s by p2, where our p1 is equal to minus s1 and p2 is equal to minus s2, and omega z value, the 0 frequency, you look at the 0 frequency, that is at Ki Fref by Kp, omega z, okay, Ki Fref by Kp, and this is also Ki Fref by Kp. So, omega z is same as P2. If that is the case, what you see is in this transfer function that these two, this is approximate, no one is denying that, but it works quite well. So, you have P1 as a pole. What was this earlier? This was the unity gain frequency for the loop gain. So, coming back to our NTF of TDC, the bandwidth of this transfer function, bandwidth of this transfer function is same as the unity gain bandwidth, which is k TDC, k DCO, kp. Why I derived this particular value? The reason is that if you have the quantization noise, the quantization noise goes through this path, the path which is highlighted here in yellow, right, and you have a large gain, you have a large bandwidth. So, you have a large gain, and when you have a large gain, you actually have a lot of noise at the output. So, the only way we can reduce the contribution is by reducing the bandwidth. K TDC, given the number of bits in the TDC, you can't do anything. K DCO is also limited to be tuned. Kp is something which you can control. So, you have to reduce the gain. Okay. So, what is the minimum gain we can have? The minimum gain which we can have to reduce this contribution of the quantization noise at the output is actually 0. There is nothing else you can, nothing better which you can do more than that. So, if I do that, let's bring this here. So, as I said that the minimum gain which I can have for the quantization noise from the proportional path, that is 0. So, I just remove the path altogether, make it 0. What's big deal? Well, if I do this, I have 2 integrators in the path, okay. And when I have 2 integrators in the path, then it will also become a problem. The loop is not stable. So, then I say no, see, with the analog PLL, we had proportional path, and with respect to that proportional path, there was no quantization error in the phase error detection. So, we will try to do something like that. In measuring here the phase error using PFD, there was no quantization error. So, we go and insert this PFD, okay, and this reference signal is same going to both the cases, and feedback signal is also going to be same. Like this. So, this gives me phase error. Now, this phase error I have to somehow control my VCO. So, you can say you had this DAC output already, okay. The previous one, this is nothing new which you have seen. This DAC output, you add the proportional path gain somehow. This PFD output has to be converted to some using some DAC, because the summation is happening with the DAC voltage or current. PFD gives you up and down. We do not know how to do it right now, but we are just assuming if it is possible. They come to a DAC. I call this DAC as P DAC because it comes in the proportional path, and then it gets added up here. The previous DAC is now coming only in the integral path. So, I start calling this as I DAC. Okay. Now, you look at this particular PLL, well, it is having analog phase error detector or PFD, and then it has DAC which controls the VCO. In the integral path, it has a TDC. Okay. And TDC quantization noise appears only in the integral path, which is like having a lower gain. Okay. How it is having a lower gain? Now, look at it. The NTF of the TDC now, okay, has the forward path gain with this part. Okay. So, forward path gain is only this, which is your Ki times 1 minus Z inverse, okay, times your Ki DAC, okay, Ki DAC times K DCO over S. This is the forward path gain, and the closed loop gain which you are going to see, the loop gain is for the whole loop. So, what is the loop gain? I will break the loop near either the phasor detector or at the output. I break the loop here, I go back and see what comes back. Well, it comes through two paths, it comes like this and it also comes like this. It gets added up and then finally, after adding up it appears here. So, loop gain is only not for the integral path, it is for both the paths. So, you are going to see the combined loop gain, and what we assume is that we want to keep the same loop gain for a better same loop gain or the loop gain which helps us to minimize the output jitter. So, you have this. Okay. Just consider this particular transfer function with the previous one, where you had is the same thing, but initially you had this particular K p in the numerator also. Previously it was this, okay. Now this has become 0. Okay. So, when this becomes 0, your NTF TDC, actually your noise contribution at the output of the TDC reduces, right. Now, well, this is good. It helps us to reduce the quantization, TDC's quantization noise contribution to the output. This problem is solved, but the other problem that your TDC, if you want, still it is some quantization noise, and if you want to reduce that quantization noise, then you have to reduce Q TDC, and this is there was a power versus quantization noise trade off. So, you can say previously the quantization noise contribution to the output was much more, it has reduced, but it has not become 0. It is not like your PFT stuff. Okay. So, here what one can do is one can try to reduce the power consumption in the TDC, reduce your Ki gain to reduce the contribution to the output. Okay. So, in order to make our PLL more power efficient, what we can do is we can go ahead and use a 1 bit TDC. Whatever TDC you are using, now it seems like you are measuring the phase error in two different forms. One you are using through PFT, other you are using through TDC. If I do that, and that too using let us say with our 1 bit TDC, or just an example, it is 1 bit, let me write it first, it is 1 bit TDC. Okay. So, here we feed the reference to both. One thing which is going to hurt that to measure the same phase error, why do we need 2 blocks? Well, one, we need a digital input, that is why we need 2 blocks. So, this goes through your Ki, or you can say you have quantization noise of the TDC getting added here, you go through Ki, then you have the integral path which is like this with Z inverse coming back here with your IDAC, okay, and outputs of this they go to, because PFD gives you up and down, I have to somehow convert, I do not know how, but we will find it. PDAC and IDAC, you have an oscillator, they are getting summed up before you feed into the oscillator, and then you have VCO. This is your feedback path, divide by n. Okay. Here you add Q TDC, this is your reference. Okay. So, now the same phase error is measured using PFT and 1 bit TDC, and you do add the quantization noise at the output. Now, if we try to reduce the power consumption in the TDC by using 1 bit, we know that the range of this TDC is very limited. Okay. It is like going for, it can measure, this particular TDC can measure phase error only between minus pi and pi. Okay. So, this is what we have. This is the TDC 1 bit TDC output. Okay. So, with respect to phase error at the input. In contrast to this, so let me first write our TDC output as DTDC, which is still, whether it is 1 bit or it is 10 bit, it is the same, right. The signal name here is the same. So, this is minus pi, this is plus pi, such kind of phase error detector limits your pull in range, because you know positive phase error, your TDC output is actually becoming negative with an average value of 0 for 0 to 2 pi. This is going to create a problem. Okay. In contrast to this, you have seen earlier that the PFT output has been something like this. So, your PFT output has been like this, which was giving us a proper, this is your PFT output, this is your TDC output. So, now the question is this 1 bit TDC, which helped in reducing the power consumption in the TDC, and having TDC only in the integral path helps us to reduce the quantization noise contribution to the output, but now it is limited by the pull in range for the oscillator, for the PLL. Okay. So, what we need to think about is that how I can extend the range of the 1 bit TDC. So, now if you think about it, the output of your PFT, which is up and down signal, right. The average of up and down signal is VPFT output. This is nothing but your average of up minus down. If the phase error is positive, in that case your up minus down signal is always, average is always going to be positive. If your phase error is negative, average of up minus down signal is always negative, and these up and down signals are independently, they are clock signals, they are not the voltage signals, by the way. They are not like analog voltages, they are proper clock signals like this, right. So, if I can convert somehow I can convert this magenta one, which is our TDC output, for positive phase error. If I can convert positive and negative phase error, is if I can convert like this, that is the best option, because then, well, you will have the quantization noise, but you will not have the, there is a lot of quantization noise because it is 1 bit, but for positive phase error you will always get positive, for negative phase error you will always get negative. Okay. There will not be any pull in range issue. So, what we can do is, you try to think that this PFT output, it is always positive, and it is actually these two signals are giving you this PFT output, right, and these two signals are clock signals. If the difference, this timing difference is positive, they give positive. So, what we want is, if phase error is positive, For TDC we always want only positive. What we can do is we can take these PFT outputs, you have reference and your feedback signal. PFD outputs are up and down, and these PFD outputs can be used to clock the 1 bit TDC. Okay. So, here I am just, this is what you have. I will just take these signals up and down, and these signals go to 1 bit TDC, which is nothing but like a D flip flop. So, this is clock, this is D, this is Q, you get an output, and now this output I call as D TDC. Okay. So, you look at it, if here my up comes first, that is at D, my D down comes later, which is here. So, down is going to sample the up. If the phase error was positive, I will get D TDC as 1. If my phase error would have been negative, something like this, then I would get 0. So, you get 1 bit output at D TDC, right, while having the range which is the same as your PFT, it is an infinite range. Okay. So, now we can include this particular block in our PLL. So, previously we had this as the PLL where we tried to reduce the contribution of the TDC's quantization noise. Now, we have moved a step further and we are removing this TDC from here, because you still have to, you are having a trouble with the pull in range. We get this. Okay. So, now you have this, these up and down signals, they go here, TDC output is this. This is your feedback signal, and this is your reference. Okay, this is output. Now, this particular PLL, okay, is called as a hybrid PLL because it has analog and digital both. Okay. So, what you see is in the proportional path, to highlight it, I will do that. In the proportional path, your phase error directly comes to PDAC and to the summing voltage. In the integral path, what you see is you get the phase error digitized to 1 bit, goes to the integral path and comes here. Okay. So, now this particular PLL has unlimited pull in range, it is not limited by your any sort of TDC issues. Okay. Now, well, we are done with this hybrid PLL block diagram. Now, let us look at the quantization noise and other stuff, which the noise sources which we have now. So, I will just write as QTDC. So, for your small signal block diagram, I have measure my phase error between the reference and the feedback. This is plus, this is minus, this is my phase error. PFT block we have seen it is 1 over 2 pi, that is the gain. Then you have PDAC. So, right now this you get this your whatever the phase error you get, it goes to PDAC. PDAC has gain, let us call that as K times PDAC. Okay. It goes here. The output of the PFT, it comes the phase error, whatever phase error you have, that phase error goes through the TDC, it has the TDC gain, K TDC, then you add the TDC quantization noise as Q TDC, it goes through the integrator which is K I by 1 minus Z inverse. So, I will write here K I F ref by S, then it has the DAC gain which is K I DAC, these two add up here. Okay, when you have the DAC gain, you can actually have the DAC quantization noise SQ DAC, okay, and this SQ DAC actually adds here, and then you have K VCO over S. This comes back in the feedback. This is the small signal block diagram of the hybrid PLL. Okay. Well, there is the phase noise of the VCO which I will add as VCO. So, now you see that the TDC quantization noise is not present in the proportional path at all. Okay. So, with the given noise sources, we can find the noise transfer function for both of these, right. And as I told earlier, the noise TDC which we are the NTF of the noise transfer function for the TDC, this is quite important. Okay. The DAC quantization noise, well, whatever you have, let us just write that as S of I DAC. This quantization noise will come and this is going to be band pass filtered here. Okay. So, when we are looking at different contributions, we need to just write our NTF of, now what we are going to have is NTF of TDC, and we wrote that earlier. NTF of TDC is K I F ref by S times K I DAC into K VCO by S whole divided by 1 plus loop gain. Okay. And in this case, the loop gain is going to be this little complicated. So, I am going to break the loop here. Loop gain is going to be 1 by 2 pi times K P DAC times K VCO over S, this is 1 plus your K TDC times K I F ref by S plus K I DAC times K VCO over S whole divided by 1 over n. Okay. So, what I see here is now it is quite common to, when you are implementing in this manner, your control of the oscillator is not the voltage control, because it is easy to sum of the current. So, we may use a current controlled oscillator. As I told earlier, you can have a voltage control or you can have a current control. Using a current control oscillator will be easy here. So, I am just writing it in a different way, that you have 1 by 2 pi, the proportional path gain is K P, then you have K, this is K P, let us keep this same way, you have K C C O in place of V C O. Now, K T D C, K I and K I DAC, all these gains I am just summing them up and writing them as K I dash, okay, times K C C O over S square, okay, by 1 over n. If you plug in all these values in your NTF TDC, what you are going to find that this NTF TDC with respect to omega, okay. The NTF TDC with respect to omega, this is going to be a low pass transfer function, okay. And this particular low pass transfer function has two zeros, two poles like this, and the first pole will appear at your 0 frequency omega z, okay, and the second pole will appear at the frequency, the unity gain frequency for the loop gain. So, this is what you get, and then the TDC quantization noise which you have, that quantization noise is actually flat. So, it is getting filtered by TDC, this is TDC noise, it is going to get filtered by your low pass transfer function here, which is where the pole frequency is, the dominant pole is coming, is the actually the 0 frequency. Okay. Previously, we had seen that the dominant pole for TDC's dominant pole while filtering TDC's quantization noise, when you had the TDC quantization noise going through proportional and integral path, was the unity gain bandwidth. Now, that has reduced to the 0 frequency for the same PLL. So, TDC noise gets more filtered. Okay. So, in this way we can design, now choosing all these parameters, we can get the same PLL performance as we were getting for the analog. Now, how to control the oscillator and other things, this is these are things which we need to look, we will see in the next session. Okay. Thank you.